I would like to do a little bit of, how about Washer's Redemption? I still feel badly that I messed it up last time, and we did one more example after I messed it up, but I think it would be a good idea for me to sort of clarify things and hopefully help this all to come together for folks. These things, the volume according to the Washers, of course, this is the formula. It's pi integral a to b of what we have in here is the outer radius squared minus the inner radius squared dx, where outer and inner are formulas for the two radii. And they are formulas involving x, although in most examples, like one or the other will be a constant. But it can be that actually both are functions of x, all right? And what I will say about this is the setup can be hard. Once you set it up, usually it just turns into a more or less ordinary integral, which you can do by ordinary means. But the setup sometimes is hard. So I have prepared 7 more examples that we're going to do just the setup of. So, and hopefully we will get some kind of general feeling for how these go. Of course, to compute it all the way to the final answer is a little bit more work, but that's the easy part for problems like this. So let's try. All of these problems is just about revolving some kind of area around some axis and finding the resulting volume. So how about this is y equals x squared. And I am looking at this piece of area here and revolving this around this line, y equals minus 1. All right, so this is revolved around in that way. So this is like one of those sort of, I keep calling this like a Christmas tree stand, sort of a cone-like thing, but with the center drilled out of it. All right. So really, as far as the setup goes, all I care about is what's a formula for the inner radius and a formula for the outer radius. And specifically, what I mean by this inner and outer is the inner would be the distance from the rotation axis, sort of to the innermost wall of that shape that you get when you rotate it. That's the inner. And then the outer, so this is the inner, and the outer is the distance from the rotation axis to kind of the outermost wall of the shape. This is the outer, all right? Now sometimes by some kind of common sense, it's easy to say what one or the other or maybe both of these are. Like for example, in this case, I think it's easy to say what is the inner radius here? You can show me on the fingers. It is 1. Yeah, just on this picture, just because the function is up here, but right here, as far as the inner wall here, this distance is always 1. So by sort of common sense, this is not so hard to say. Although in some examples, it's a little bit more complicated. So I would like to suggest if you cannot just do this by some kind of common sense, and last time I had sort of a failure of common sense, one way to think this through in a very systematic way is just to compute the height of each of these line segments by taking the top, the value at the top, and you subtract the value at the bottom. So these heights can always be, if you are having some kind of lapse of common sense, these heights can always be computed like the actual value at the top minus the value at the bottom, right? And so the inner, in this case, if you think it, now this inner is easy to do by common sense, I think, but if you want to think this through in this very like structured way, the top of this is at y equals 0, and the bottom of it is at y equals -1. So I would say the inner radius this time is 0 minus -1. Because the top of that inner radius is at y equals 0, and the bottom of it is at -1, which of course equals 1, that's the common sense answer in this case. All right, but I find it helpful to think of it in terms of this top of the line and the bottom of the line, and you just subtract them. All right, so in that same way, what about the outer radius here? Thinking of it in terms of the top minus the bottom, the top of this segment here is at the function y equals x squared. So the top of that part is just x squared. And then I subtract the bottom of it, which is at y equals -1. So writing it out like that, it's like this, which is, simplifying here, x squared plus 1. All right, I hope that that's clear. I find that when you think of it in terms of like the tops and the bottoms, everything seems, at least to me, it seems to clarify things. All right, this is like rapid fire, several more examples of this type. How about, this is what I mean, I just want to do the setup. So just deciding what the inner and the outer is. Once you know that, you plug everything into the formula and it works out great. How about this one? I'm using this same parabola again, y equals x squared. This time the region that I want is over here. So this part of the area, and then rotating around this axis at -2. All right. Again, the inner thing, you might find it helpful to draw a little picture here. This is the inner, and this is the outer. This is very similar to the previous one. Anyone want to tell me what's the inner radius here? 2, they are saying. Yeah, this one, again, by sort of common sense, you can just see on the picture that is distance 2. But if you prefer, you could say the top of that inner segment is at y equals 0, and the bottom of that inner segment is at y equals -1, which makes 0 minus -2. I just said -1, I meant -2. 0 minus -2, which is 2. Okay, and the outer? Anybody want to say? X squared plus 2, she said. Yeah, the top of this segment, this longer one, the outer segment here, the top is at x squared, and then I'm going to subtract off the bottom, which is at -2, also known as x squared plus 2. Yeah, I hope everybody's feeling it. All right. Maybe, so I have 4 more. Maybe I could give those for you all to try and see how you like it, how you like me now. I hope you like me better than yesterday. How about, I've been somewhat unimaginative and I'm using y equals x squared for a lot of the functions. I mean, it really doesn't matter that much. So here's y equals x squared. This time I want this area, but this time I want it to be rotated around this axis up here. So the shape now doesn't look like a Christmas tree stand anymore. It looks like the edges of it are kind of like basin shaped, although it's got a big hole in the middle. All right, this is y equals 3, so rotate it around there. And I'm going to continue drawing some other examples. Here I felt cute. I made this y equals -x cubed. Doesn't really matter. I'm going to try to put 2 more on the screen here. Feel free to chat with your friends if you like. This one's a little strange because the shape I'm talking about is like floating up there in the air. Don't worry about it though. Let's see what you think. Maybe I'll come around and see how you're doing. You don't have to work out the whole problem. Just tell me what the inner radius and what the outer radius is each time. And I hope my pictures are clear enough. Please let me know if something doesn't make sense. So this is touching the graph.
Yeah.
So you just use the graph is x. So it's going to be 3. Right?
So for the outer.
Yeah, so that, this is this one.
Yeah.
That's the top is 3. So the outer one, the top is 3. And the bottom is over there.
Oh, yeah, 0.
Okay. Segments I'm talking about. The one is from here to Doing okay? Yeah, doing all right here? Okay. Doing good? You good here? Okay here?
Yep, good.
How's it going? Good. I'll give you another minute and then we can talk about them. Because I do want to move on to the cylindrical shells. Oh, your minute is up. I'm going to spread these out a little so I can write next to them. So this first one here, if I were to draw sort of the inner and the outers, sometimes it's a little tricky since this one has the axis on the top. The inner is actually the one that goes to the curve, and the outer is the one that goes all the way down to the sort of the outer edge of this thing. So here is the inner, and here is the outer. But anyway, the inner in this case, I would look at it's the height of that, the shorter of those two segments. The top of that segment is at y equals 3, and the bottom is at the curve, which is x squared. So this is 3 minus x squared. I hope that's what you said. And the outer, the top of the outer segment is at the 3 also. So this is 3 minus this outer segment goes all the way down to 0. And so it's 3 minus 0, which is 3, right? That one also you can kind of common sense your way through that one. I hope you got those same ones. All right, how about the next one? This is somewhat strange because the thing is floating in air, but actually it doesn't really matter. This is the inner and this is the outer radius. So the inner in this case, actually this inside distance is always going to be 2 in this case. But if you like to think of it in terms of the top minus the bottom, the top being 1, it would be 1 minus the bottom, which is -1. So I'll just write it like that to be totally clear. But that's 2. And then the outer would be the other segment, which goes all the way up to the curve and then down to here. What'd you get for that one? Anyone want to say? Yeah? X squared plus 1, he says. Yeah, the top of this is at the curve, which is x squared, and then the bottom of it is at -1. So this is x squared minus -1, which is x squared plus 1, like so. Is that exactly the example that we did last time? It's something like that, at least. It was very similar, and I messed it up. I got to stop beating myself up so much, right? I need to talk to Stacy about this. Remember Stacy? This is a reference to first day of class. Yeah, you got to keep up with with my mental health references. Okay, what about this one? The inner and the outer. In this case, I would say, again, just doing like tops minus bottoms. The top here is at y equals 2. The bottom of the inner segment is at 0. So this is just 2. 2 minus 0, which is 2. The other one goes from 2 all the way down to the curve, which is negative x cubed. So for the outer, I would say it's 2 minus negative x cubed. In other words, 2 plus x cubed. I hope that's what you got. And then the very last one, this may be the most interesting one. In this case, the inner radius and the outer radius are both not constants. Neither of them is just a number. They both involve x's because both of those lines go up to one or the other of those two curves. So the inner one is the one which goes up to the parabola part. And so the top of the inner curve is x squared. And then I subtract the bottom, which is just negative 2. So this is x squared plus 2. And the outer radius would be going all the way up to the straight line, which is x. That's on top. And then again, minus negative 2. So this would be x plus 2. And I hope that's what you got for all those. Anybody got any questions about this? I hope that this is clearer than I was being yesterday. I got just one more, just for fun, because I want to relate this to the cylindrical shells thing. I thought it might be fun to try. How about this being root x, and then I would like this area here, this is from 0 over to 1 and up to 1, because the squared function hits 1 comma 1. So this area right there. And then rotated around just the x-axis as the axis of rotation. So what it looks like is this kind of it's like a bowl-shaped or a straight cylinder on the outside, but the inside of it has this carved out parabola on the inside, all right? I hope I haven't ruined the picture. Maybe I'll take those lines out. Okay, anyway, let's just try and set this one up also. So in this case, my radii, if I were to draw the segments, is like that's the inner segment and that's the outer segment, right? Anyone want to give me? Somebody shout it out. What's the length of the inner segment? Square root of x. That's the top of the inner segment. The inner segment, I mean this shorter one here, it goes up to the curve, so its top is at root x and its bottom is at 0. So it's root x minus 0, which is just root x. And then the other one, the outer one, what do you say?
1.
Yeah, just 1. The top of the outer one is always at 1. If you like, you could say 1 minus 0, which is the bottom of it. Anyway, it's 1. All right. Now this one, just because I want to relate this to something else, let's actually try and do the whole thing, not just the setup. It's an easy integral anyway. So we get pi integral a to b. Can anyone say what are the a and the b here?
0.
Yeah, 0 to 1. A to b is the range of x values that it takes to cover up this shape. And the x values here go from 0 to 1. Coincidentally, the y values also go from 0 to 1, but I'm looking at x values there. And then I go outer squared minus the inner squared, right? That's the formula that you use for one of these volumes with the washers. It's the outer squared minus the inner squared. And I like to see root x squared because the square root will go away. So this ends up being just pi integral 0 to 1 minus x dx. And this is a very easy integral to do. I leave the pi out front. Any derivative is x minus 1/2 x squared. And I'm going to plug in 0 and 1. When I plug in 1, I get pi 1 minus 1/2, and then subtract. I plug in 0, I get pi 0 minus 0, right? So this goes away. My final answer is pi times 1/2, right? Pi times 1 minus 1/2, which is 1/2 pi, if you like. That's the area of this weird bowl-like thing. It's like a salad bowl where the edges are flat, but the inside is bowl-like. All right, great. Let's talk then about the cylindrical shells thing. I want to try to pick up where we left off last time. Now, last time I gave some kind of vague explanation of the method, but the upshot was, I will tell you sort of, well, let me just draw one picture and then I'll give you the formula. We don't need to talk through the entire thing again, but this was an example of this parabola, x squared, and rotating, taking this part of it, this just 1/2, and then rotating this around the y-axis. It makes, actually this is the same shape as this, it's just turned sideways. It is again one of these sort of bowl with straight sides around the edge, but it's a parabola type cavity in the middle, all right? And the idea behind the cylindrical shells method is, as usual, this is like the standard idea behind all of calculus. I cut this thing up, but instead of slicing the 3D shape into washers, I'm going to slice the original 2D shape like this into rectangles and then rotate each of the rectangles. Yeah.
Do you use this when you rotate around the y-axis?
No, you can do it sort of sideways by solving all your equations for x instead of y. Yeah, so you can do it either way. But in most cases, if you do it using the shells, you could have also done the same shape using the washers and vice versa. Although sometimes it turns out to be easier using one or the other of the methods. But the idea is you chop up your original area into rectangles, just like you usually do doing calculus. And those rectangles, when rotated around the y-axis, they give you this cylindrical shell type shape. And then you add up the volumes of all of the shells. This is a little weird, but I will just tell you the sort of formula that you end up with. We talked about a little derivation of this. It is, maybe I'll put pi on the outside, x f of x dx. This is the cylindrical shell, sorry, it should be 2 pi, not pi. It's 2 pi because this comes from thinking of these shells. What's important about these shells is the circumference of that circle. That's what gives you all the volume of those shells. And the circumference of that circle is 2 pi times the radius. And the radius here is x. That's why there's a x here. And the height of the shell is f of x. That's why there's a f of x here. But anyway, that's the formula. Of course, integral from a to b. And you have to remember, in this case, a and b, a represents the middle of the shape. So even though this shape, when you revolve it, it sort of starts over here and ends up over here. But the a and the b that's used in the cylindrical shell formula, the a is the x value representing the center of all of these shells. And then you go up to the y value, which is on the, not the y value, go up to the b, which is on the outer edge of these things. So a is the x value of the inner edge, and b is the x value of the outer edge. This is different from the washer thing. All right? And so in this particular example, when you set this one up, what it looks like, just plugging into the formula here, I get volume is 2 pi integral. What should I use for the a and the b here? Actually, I didn't really say. I intend for this point to be at x equals 1. So the a and the b are, yeah, it's going to be 0 and 1. Inner edge maybe is a little, is it strange how I said that? Maybe it is. It's clear to me, like for this shape here, 1 is the outer edge of that shape. The inner edge, I mean, starting sort of from the middle, it would be 0 in this case. Maybe I'll just to clarify, the middle, all right? You are not looking for the value all the way over here, which would be -1. You'll get the wrong answer if you go all the way from -1 up to 1. It's not so. You want the value in the middle. Okay, so 0 to 1. And then the rest of it is just, x times f of x, which is x squared dx. All right. Now, I said before, I mentioned, this shape that you get here is actually, it is exactly the same shape as that. It's just turned on its side, right? Here I used the formula x squared. Here I used root x, which is the same formula but sideways. So if we calculate this out, if we did it right, it should equal that, right? So hopefully, can we just work it out and see if we get the right answer? The right answer should be 1/2 pi if all of this is correct. So just to simplify before doing the integral, it's 0 to 1 x cubed dx is what I'm integrating. That's x times x squared. And then the antiderivative, x cubed gives me 1/4 x to the 4. So this is 2 pi times 1/4 x to the 4, evaluating at 0 and 1. So I go 2 pi times 1/4 times 1 to the 4 minus 2 pi times 1/4 times 0 to the 4. This is 0. The first part, those ones are all ones. It's 2 pi over 4, which is 1/2 pi yet again. Great. I will circle it. That's how satisfied I am that I got the same answer. All right. Like I said before, most shapes, just most shapes that you encounter, you could use either of the two methods. Oftentimes, one will be more convenient than the other, and I'll leave it up to you to decide. You know, was this way of doing it easier than the washer's way? To me, in this particular problem, there's no clearly easier or better way to do it. Yeah.
Up there, yeah, you go from x minus x squared to x cubed. Is there like a minus situation there, or?
This is times.
Oh, okay.
Yeah. So the formula in general is always this: x times f of x.
Gotcha.
Yep. Why is there an x in there? The short answer is because that's the formula. Although it comes from the fact that x represents the radius of these shells, but I wouldn't suggest that you think it through every time. I would just suggest you remember the formula here. All right. Excellent. By the way, I'm not big on making you all memorize formulas, like lots of formulas, although I would expect you to know this formula, say, on our quiz, I suppose, next week. I think because the quizzes are going to be very kind of narrow focused, there should never be a time when you have to memorize like 20 different formulas. But you know, one at a time, two at a time, I'm a little more comfortable with. So I hope that is all right with you. If you're ever concerned about, am I supposed to know this or that, I would be happy to tell you. All right, let's just try a few more examples. We got like 20 minutes left. I think we can do a few more examples of the cylindrical shells method. Let's try it. Here's an example. Actually, this example is one where the shells is actually a lot easier to do than the washer method. So let's try another one here. How about, I'm just going to do the setup for this one because actually doing the integral is a little bit of a pain, and I don't want to get into it, but let's try this thing. This is one lump of the function y equals sine x, and I want to rotate this around the y-axis. All right. Can anyone describe maybe in words what this shape looks like? I don't know how easy or hard that is. Like this. Maybe tempted to think this looks like a certain anatomical feature, but it's not that actually. It doesn't. This is not that dump truck, as they say. Can anyone say what it?
It's like a fruitcake.
Yeah, like a fruitcake. Yeah, that sounds like another euphemism, but I mean like a real something like in a bunt cake, right? One of those like ring-shaped coffee cakes. That's what this looks like, kind of, right? Yeah, that's what I'm talking about. Because it's rotated. It's not like each of these things is its own nice little shapely thing. It's like this, right? Okay. Anyway, let's find the volume of that fruitcake. This is a nicely set up to use the cylindrical shells method because you can imagine sort of one side of that fruitcake. I cut it into these little rectangular things, which make nice little rectangular shells or cylindrical shells that build up that whole shape. All right. So my function, I'll just write the formula and then we'll try to plug stuff in. A to b x f of x dx, right? So f of x is sine of x. That's what the function is. What should I use for the a and the b? I think the a is obvious. The b you have to think a little bit. Yeah, he said 0 to pi. So 0 in the middle, that's 0. You have to think briefly about how far down actually is that, but I hope you remember your unit circle or whatever. This is x equals pi is where that bump comes back down to the bottom. All right, so this is going to be pi integral 0 to pi x sine of x dx. And that's it. I mean, this is the setup, if all you care about is the setup. Yeah?
Should it be 2 pi?
2 pi, yeah, sorry, I left out the formula itself has a 2 pi in it, not pi. That is easy to mess up. The washer formula is just pi. This one is a 2 pi. The reason is because the washer formula is based on the area of a circle, which is pi r squared. The shell formula is based on the circumference of a circle, which is 2 pi r. So that's why this one is a 2 pi and no squared. The other one has just a pi and a squared. All right. This integral, unfortunately, is kind of a hard integral to do. It's not that hard. You have to use something called integration by parts, which we are going to talk about eventually, but we haven't done it yet. So let's just leave it at that. I will just say at this point, this is a hard integral. If I really want to, on our test or something, I might just say, give me the setup and leave it at that. Or if for some reason the integral turns out not to be so hard, I'll have you do the whole thing. All right. Any thoughts about that one? Great. Let's try. How about one of my favorite sort of Christmas tree holder kind of shapes? So let's try the shape you get by rotating this thing, so this line, but I only want that much of it. I usually draw this as being red. This much of it, and then rotate it around the y-axis. All right? Where this line is y equals 2 minus x. I didn't quite get the scale right on my picture, but I suppose it doesn't really matter, but it should be kind of closer to there. All right, and this, if you spin that triangle around the y-axis, you get one of these sort of cone-shaped Christmas tree holder kind of a thing. But anyway, the formula, 2 pi integral a to b x f of x dx. This one I think we can actually do the whole integral. What you end up with is not so hard because it's a polynomial. 2 pi is like so. What do I use for the a and the b? Yeah.
2 and 0.
It's not quite 2 and 0. It is 2 is the outside, so the upper limit is 2. The inside is, yeah, it should be 1. This is kind of what I meant by it's the distance from the inside to the outside. Now in all the other examples, the inside has been like all the way down at 0, so it's kind of like the middle. But we only want to consider this portion of the triangle. If you really went from 0 to 2, you get the entire cone, which is not what I'm trying to talk about here. Okay, and then x, and then f of x, which is just a function. All right. People have different opinions about this, but you may get the feeling that setting these up is easier than the setting up the washer method. I don't know. It's just another way of doing similar type problems. This one, let's try and actually do this. How would you do the integration here to find the antiderivative? Yeah. Yes, I would first distribute the x. When you have multiplication inside the integral, you're going to have to do some kind of a trick. In the worst case, multiplication inside might require u substitution, but not this time. We can simply distribute, and now it looks like a polynomial in there, so we can just do our antiderivative as usual. So I get 2x becomes x squared, right? And then minus 1/3 x cubed. And I'm plugging in 1 and 2. It's 2 pi, 2 squared minus 1/3 times 2 cubed. Subtract 2 pi, 1 squared minus 1/3 times 1 cubed. Like so. And I would leave it at that on a test. All right. I hope that looks good. Great. I got one more. Oh no, I got one more and then I have one for you to try. Good, I was worried we got extra time. How about I thought it would be fun to try the area or the volume of a donut-like shape. I don't know if you've ever heard of a formula for the volume of a donut-type shape. Anyone know the fancy mathematical word for a donut-type shape? This is an annulus is like a two-dimensional. This is what the word I said last time. An annulus is a flat thing like that. I'm referring to a three-dimensional donut sort of a thing. Anyone heard of this? So that's an annulus. I would like to talk about a donut shape, which is referred to as a torus. And free of charge, I want to show you all how to draw an awesome looking torus. You ready for this? This is you can amaze your friends. Check this out. Start like this. All right? You with me so far? And then you do this. Doesn't look like much yet. Watch carefully. Now you do that. Yeah. It's pretty awesome. Very easy. Show your friends at dinner. This is how you draw a torus with only 3 strokes of the pencil. Anyway, I would like to find the volume of such a thing. Now, the important quantities which govern the shape of this torus. Let's say I want the torus which, if this is like the origin in 3 dimensions, I want the torus where this point here is distance 2 away from the center there, and then the radius here is 1. I think that's enough information to describe exactly what kind of torus I'm talking about. All right? Where this radius of 1 is like the radius of one of those, the circle which defines the torus, how it goes around the origin. All right? I want to think of this in terms of the cylindrical shells. Can anybody say we need to somehow visualize this 3-dimensional shape as starting with a flat thing and rotating it around one of the axes, just like if you start with this triangle and rotate it around, you get some kind of a Christmas tree stand or whatever. How could I make this torus out of starting with something and rotating it around the y-axis? What shape should I start with? I heard somebody whisper. I think it's a circle, right? If I start with, so this, a torus, if you want to sort of build the torus in this way, the torus comes from a circle over here, right? And actually, to be very specific about it, according to the way that I said, I believe if you go 1, 2, the circle I'm talking about is there, right? The distance from the origin to the middle of that circle is distance 2, and then that circle itself has radius 1, all right? And if this circle is rotated around the y-axis like so, what you get is that torus shape. All right. So can we set up, and I just want to do the setup, but can we set up the integral to find the volume? In this case, it's a little complicated. We need a formula for the circle over here. Unfortunately, this circle is not a function, like its top half and bottom half is not a function. I think the easiest way to handle that is, let's do, I'm going to change my tune a little bit. Let's do this instead, where I only take the top half and then multiply by 2, right? So really, the integral that I'm going to do is one which finds the volume of the top half of a donut. If you were to slice it sort of the long way, I would be only finding the volume of the top half, but then you multiply the answer by 2 and you get the full volume of the torus. All right. Anyway, can we do that? So can we find a formula for this function here? This is a top half of a circle. Maybe we should just write the formula as if you were doing the formula for the full circle. Anyone remember a formula for a circle? This is a circle of radius 1, but it's not at the origin. It's somewhere else. Anyone remember how to do that? This I would not necessarily expect you to remember how to do. So the basic formula don't write this down quite, but the basic formula for a circle of radius 1 is that. But this is a circle of radius 1 at the origin. Anyone remember how do I move the center point of the circle to somewhere else?
We do like x minus 1.
Yeah, this would be, so I want the x coordinate of the center of the circle is at 2. The proper way to modify this, and this is the actual formula, is like that. X minus 2 squared plus y squared. You don't need to modify the y because the center here is still where y equals 0. So the y does not require any modifications. All right? Now, that's the whole circle. Really, we want to write this as a function, so I'm going to solve for y here, which involves subtract this to the other side and then take a square root. So my function is y equals square root 1 minus x minus 2 squared, like so. That, because I did the square root without the plus or minus, that actually is the formula for the top half of the circle. It's the top half only because there's no plus or minus. All right, and I think we are pretty much ready to set up the integral. So our torus volume is, first of all, I'm going to put a big 2 times this. Remember what I said before? It's because to make 2 halves, to make 2 halves, right? The real integral formula is going to go in here, but there's an extra times 2 on the outside, which is not part of the formula. But anyway, the volume formula is 2 pi integral something something x times f of x. Can I fill in? The f of x is this, 1 minus x minus 2 squared, and then dx. Right, that's the cylindrical shell formula. We should say, what are the a and the b for the integration boundaries? You should be looking at, on this picture, it's really from here to here. Yeah, 1 and 3, if you set up the picture correctly. The inner radius is x equals 1 and the outer is 3 here. So this goes 1 to 3. All right, and I think I'm going to leave it at that in terms of doing this. This is a pain to do. It's the very weird formula here. You could, if you really had to do this, you could distribute this, like do the FOIL here, simplify a little bit, and then do some somewhat weird U substitution. This would work out, but I don't want to get into the details. All right. Great. In our remaining 5 minutes, I had one example for you all to try. So let's see if we can do this in 5 minutes. This is a fairly straightforward example. Do the cylindrical shells thing on this shape here. So the function that I'm talking about is y equals cube root of x. And I'm going out to 1, and then take this shape here and rotate it around the y-axis. Maybe I'll give you 3 minutes to try it out, and then I will say what I think the answer is. There's not a whole lot to it in this particular example. All right, your 3 minutes are up. This one is, I would describe this as an easy one because there's not a whole lot you have to do to set it up. The formula, I will just write again, f of x. So the f of x is just this function. That's the f of x. And then the a to the b is 0 and 1. 0 is this point in the middle that you're rotating around, and then 1 is the outer, sort of the outermost radius of these shells. So it's going to be 2 pi integral 0 to 1 x times cube root of x dx. And that's really all there is to it. There's no fancy setup here. How would you do that integral if you have to do it?
Maybe x to the 1/3.
Yes, the cube root of x should be written as x to the 1/3. It's basically always a good idea in a calculus class to rewrite a radical sign as a power to some, fraction. So it's instead of cube root x, it's x to the 1/3. What can I do next to simplify?
X to the 4th.
Yes, you should add the exponents here. When you're multiplying powers of x, of course, x by itself is x to the 1. And so x to the 1 times x to the 1/3. I add the exponents, I get x to the 4/3. So I haven't done the integral yet, but this is x to the 4/3, like so. And now we can do the integral. This is a fairly straightforward antiderivative now. 2 pi 4/3, I increase the power by 1, so 4/3 plus 1, that's 4/3 plus 3/3 is 7/3. And then I divide by that exponent in the front, 1 over 7/3, in other words, 3/7, like so. And then plug in 0 and 1. So I get 2 pi times 3/7 times 1 to the 7/3 minus, all this is going to be 0. 2 pi times 3/7 times 0 to the 7/3. And so it's, I guess, 6 pi over 7 if you want to simplify. I think that's the answer. All right. Just a little heads up. My intention is for you to submit the quiz on Gradescope also, as so bring your phones or whatever. Be ready to send it on a Gradescope. Let me know if you have any questions about the quiz. And if you, I'm sorry, I meant to say this before you were all leaving. If I know some of you have accommodations for extra time on tests. If you do, please talk to me about this, because the way I want to do the quiz is just do the quiz for 15 minutes or so and then immediately continue on with the rest of class. If you want extra time, that's totally fine. We can work something out, but we need to work something out. So please let me know if that's you. You can send an email if you don't want to come and present yourself right now. That's fine.
Thank you.
Thank you.
See you.